Greetings, everyone. Welcome to this event. My name's Sam Huckabee. I'm the Dean of the College of Arts and Sciences, and it's a great pleasure, as it has been for the last this is the sixth time to open this lecture. We're very pleased to have Dr. Robert Tibshirani.
You got it right.
From Stanford, another in a list of distinguished visitors and speakers for this lecture series. And shortly, he will be properly introduced by Elizabeth Slate, Dr. Slate. But welcome to Tallahassee and to Florida State. And as you were flying over, the football team was flying out because we play Stanford tomorrow.
You're going to beat Stanford, probably.
Yeah, we hope so. We hope so. A few words about Myles. Myles Hollander, had a great career as a statistician and was a great faculty member here at Florida State University. He served, I just want to say a few words about some of the things he did. I couldn't say everything, but he served as department chair for many years. He had 19 doctoral students during his time, large number, and he mentored scores of faculty members, including me. I met him when I was a youngster early on after I arrived here at FSU. He was a good friend and a great colleague. Myles also helped to establish FSU statistics and help make it the great department that it is today. In fact, he helped put Florida State University statistics on the map. And there's a legacy there for Myles. He was recognized many times during his career with awards. I'm only going to mention one. He's a Lawton professor. That is our top award at Florida State University, internally provided. There's only one per year. And you have to do it all to become a Lawton professor, and Myles did it all. Myles was not only a great statistician and colleague, but also he was a very generous and thoughtful person. In fact, this lectureship series would not exist without Myles. It is the result of a gift he made in 2019 to endow this lectureship so that it could go on in perpetuity. And we appreciate his generosity and his thoughtfulness in providing the gift in the way that he did. So it's a great honor for me to every year to come and to kind of open this lecture. Right now, though, I'm going to turn this over to, and before I do so, I want to recognize that members of Myles' family are here. Lane, who I'm going to introduce in a moment, his daughter and her husband, Bart and his spouse. Raise your hands so people can see you. It's great to have you here. I've gotten an opportunity to get to know Lane and Bart over the last year or so. It's been a pleasure. But right now I want to introduce Lane Hollander to say a few words about Myles. Thanks.
Thank you, Dean. Welcome, guests. My dad, Myles Hollander, coined the phrase, statistics means never having to say you're certain. When it comes to my dad, these are the things I'm certain about. He loved his family and close friends deeply. He had a true passion for Carnegie Mellon, Stanford, and Florida State universities, and he believed in the limitless potential of college students. My dad loved the field of statistics and the Brooklyn, now Los Angeles Dodgers. Even though I knew my dad as something of a non-parametric statistical genius, I always questioned his hypothesis that the Dodgers had a better chance of winning a World Series game if he was not watching. My dad, a Lawton Distinguished Professor at Florida State University, deeply cherished his career in statistics. He endowed this annual lecture series to give back to FSU and to inspire students, faculty, and others around the world, just as he was inspired by eminent statisticians throughout his own professional journey at Carnegie Tech, Stanford, and as a professor at Florida State University. I've never missed a Hollander Distinguished Lecture online, and I've never understood one. Sometimes the apple falls a little further from the tree. My brother Bart and my son Connor, two lawyer apples, we'd follow online texting updates about the online cat count, stats we understood. During the Q&As, I'd cheer when Dr. Elizabeth Slate asked a great question like FSU had just scored a touchdown. My brother and I are especially grateful to Dr. Slate for her hard work and determination in making the 2025 Hollander Lecture a reality. And now it's my honor to introduce someone our dad admired deeply, Dr. Elizabeth Slate.
Thank you, Lane. So it's now my great pleasure to continue this legacy of Myles and introduce the 2025 Myles Hollander Distinguished Lecturer, Dr. Rob Tibshirani. Dr. Tibshirani is professor in the Department of Statistics and professor in the Department of Biomedical Data Science at Stanford University. Professor Tibshirani received a bachelor's in statistics and computer science from the University of Waterloo in 1979, a master's in statistics from the University of Toronto in 1980, and the PhD in statistics from Stanford University in 1984. He has maintained appointments in statistics and the biomedical sciences throughout his career, beginning with his first faculty appointment at the University of Toronto in 1985 in the Department of Statistics and also in the Department of Preventive Medicine and Biostatistics. He moved to Stanford University in 1998 and now holds professorships in the departments of Biomedical Data Science and also the Department of Statistics. Professor Tibshirani's research contributions provide novel, effective methods that have significantly shaped modern statistical theory and practice. He introduced the lasso in 1996, which is a foundational tool for variable selection in high-dimensional statistics. He has nearly 400 journal publications divided roughly evenly between statistical methodology and contributions in other biomedical areas, including cardiology, cancer research, and genetics. He is a co-author of 5 highly influential books, including Generalized Additive Models in 1990, and Introduction to the Bootstrap in 1993, and The Elements of Statistical Learning in 2001. Dr. Tibshirani has also provided leadership in our field through editorial roles with key journals, including Statistical Science, the Canadian Journal of Statistics, the Annals of Statistics, and the Annals of Applied Statistics. He is directed, by my count, 42 PhD students. Professor Tibshirani has received numerous awards and international recognition. These include, in 1996, the COPS Award for Contributions to Statistics Before Age 40, and in 2024, the COPS Distinguished Achievement Award. In 2021, he received the International Statistical Institute Founders Statistics Prize. And in 2024, among many other awards, He received the Senior Leo Bryman Award for contributions in statistical learning, statistical computing, and biostatistics. He is an elected fellow of the American Statistical Association, the Institute of Mathematical Statistics, the Royal Society of Canada, the Royal Society. He is an elected member of the U.S. National Academy of Sciences. For Zoom attendees, would you please remain on mute during the talk and put all your questions in the chat window, and we'll get to those later. Right now, I want to say that Rob's 2025 Myles Hollander Distinguished Lecture is entitled Univariate Guided Sparse Regression. Please join me in welcoming Dr. Rob Tibshirani.
Thank you very much, Elizabeth. The very nice introduction and inviting me. This is a real honor to be here. And I've had a very nice day and a half already, 2 wonderful meals and met lots of great people. Never think I've ever been here before, so it's been very nice. And it's a great honor to do the Myles Hollander Distinguished Lectureship. First of all, I actually omitted my title because I replaced it by Myles Hollander. But as you mentioned, it's the Univariate Guided Sparse Regression, joint work with Shorav Chatterjee, one of my colleagues, and Trevor Hasty, who was 2 years ago or 3 years ago gave this lecture. And this is a picture on the left of Sequoia Hall, where that's the newer Sequoia Hall. Myles did his PhD at Stanford too, in the old Sequoia Hall, like I did. We have a brand new data science building with computer science and statistics. So we've split our department now into the 2 buildings. So we have lots of nice space. Now, I didn't know Myles that well. I met Myles. He did his PhD in 1965, but he returned to Stanford a number of times. I was a grad student there from 80 to 84, and then joined as the faculty in 98. So when I was a grad student, a few times he visited, and I got to know him not very well. What I really remember, he was always smiling, very happy person. Sometimes you remember not things that you did with a person, but it's the way they made you felt. And he was really just a happy person. But I asked Brad Efron, though, who knew Myles quite well, to tell me more about Myles. So he earned his PhD, as I meant, in statistics under Lincoln Moses, who I knew well. He was one of my professors. I was there 15 years later than Myles. Some of his teachers, Myles' teachers, were, I used to call them all-star teachers: Charles Stein, Herman Chernoff, Emmanuel Parzan, and Inga Malkin. And Brad said Brad and Myles were roughly in the same class, like plus or minus a year. They kind of combined years. But Brad said his class was also an all-star class. Brad himself, Grace Waba, Joe Eaton, Howard Taylor. So it was a very special time at Stanford, and I think Myles I think he loved it there. Brad described Myles as having a dry, slow wit and was more mature than most 22-year-olds. That's what he said. But everyone liked him. That was his summary. Maybe not surprising, given what I've heard about Myles. This is a picture from a statistical science interview in 1997. That's Myles on the left, Lincoln Moses' life, and that's Lincoln Moses on the right. And this was a quote that he said about Lincoln in that article. He my role model, the statistician I most admired and tried to emulate. He showed him how to be professional, the joy of statistics, and the great pleasure of being a university professor. In my career, I've tried to do for my students what Lincoln did for me. And by the sounds of it, he did exactly that. I think Lincoln showed him the way, and Myles, from what I've talked to here, he eliminated the qualities that he admired in Lincoln. And you've already, I like the same quote, which I'm going to use, this wonderful quote. Statistics means never having to say you're certain. That's great. So it's an honor to give this talk. Thank you. And thanks for all your hospitality. I've had a really nice time. Oh, so now I'll get to the talk. And these are my office. The office to my right and the office to my left are Trevor and Shorav. Trevor, of course, I've worked with since we were graduate students in Stanford in the 80s. And we've written 79 papers and 4 books together. Shorav, who's a probabilist, I've never worked with before. He's a brilliant mathematician. So one day I walked in with this problem from the talk, and I said, "Could you prove something?" And he did a beautiful job. And I'll talk a little bit about that, but it's been a really nice experience. So this is about the lasso, sort of a new form of the lasso. So just to remind you what the lasso is, it's a linear regression model with a penalty. So in the Gaussian case, we minimize the sum of squares, subject to an L1 bound on the coefficients, right? And the way I describe this sort of in words is that, you're going to do prediction. You've got data trying to pick Y from X, and you've got to set some coefficients, but you have a budget to spend, right? If the budget is unlimited, you'll just do least squares, right? But for example, if the number of observations is greater than the number of features, you can make this 0. You can overfit it, right? If you don't have a budget. But if I give you a budget and say, okay, you can't spend more than $10 here, the budget's going to be 10, that's going to force you to pick where to put the weights. And you're going to put the non-zero weights on the features that are most predictive and put 0 weight on the ones that aren't predictive, right? And as you make the budget smaller and smaller, you get a more and more sparse solution. You get more and more zeros because you don't have as much money to spend, right? That is sort of in intuitive terms for the people who want to understand statistics. This is, I hope that's kind of clear. It's basically trying to do good prediction under a budget. And the tighter the budget, the more zeros you get in the betas, called a sparse model. And that's good for interpretation too, right? Because, investigator might start with 100 features and you tell him, well, here are the 10 important ones. The rest have 0 weight. And that's determined by minimizing this with a budget. And the budget we pick by what's called cross-validation. So we leave out some data, we try different budgets, and then we predict the left-out data and see which one does better. So the penalty gives sparsity, feature selection. It's a convex problem, which means it's good for computation and theory. So we can solve this problem for like hundreds of thousands of features and observations. And our lab has written an open source package called GlimNet. It's been around for about 15 years, which is widely used. It solves this problem for lots of different families, all the GLM families, survival analysis, etc. And we might not have heard, it's available on CRAN. There's a new package called Adderley, which does group lasso and group lasso very efficiently. And it's available also in R now too. So if you're interested in the group lasso especially, this is a very efficient new package for group lasso called Adderley, both in Python and R. And by the way, it's a big audience, which I appreciate. I do like questions, so if it's okay, there can be some questions. If there are questions of clarification, especially, there's too many questions, we can defer to the end. But this is just sort of a brag slide. This is the number of downloads of GlimNet from CRAN from its inception to now, and it's really about 8 million. So it's really still very popular. We're still developing it and adding new features. So today I'm going to talk about a new kind of lasso which relates to the original lasso. So here's a motivating example. So this is data on protein biomarkers measured on 559 protein biomarkers measured on 81 patients, 20 of them healthy, 61 with cancer. I'm not giving much details because this is with a collaborator and the data is not published yet, so they don't want me to release the details. But this is the description of the data. We're trying to discriminate these classes based on these markers. And when I ran the lasso with cross-validation, it shows 12 biomarkers out of the 559. Here are the coefficients that we found. Okay, these are the weights, the betas. I also put alongside it the univariate coefficients, so of each of the variables, the univariate least squares coefficient. And what you see, and this is not surprising, not unusual, you see there's a sign change in these two markers. This guy's positive on his own, but is negative in the multivariate model, and this guy's vice versa, negative on his own, positive. Well, we know, like we tell our collaborators, we tell our students, this can happen because of correlations among predictors, right? So when you adjust for something, the sign might change. So it's a fact, but it's also very bothersome, right? Because, for example, if you have a variable like age, which is, say, positively correlated with some disease, which it often is, positively correlated, and then you put it in a model with 10 other factors, all of a sudden it has a negative coefficient. So you tell an investigator, well, looks at being older is better for this disease, which unfortunately is not usually true. And you explain, well, that's because it's correlations with other predictors. We've adjusted for other predictors. Well, that's true, but it's really not very satisfying, right? So what this talk is about is actually not letting that happen. That's one of the main things. So unit lasso, which I'll describe in the next few slides, I'll just show you what it gives. It gives 9 biomarkers, and I've labeled them differently because there's only 2 biomarkers in common. 1 and 3 are the same as H and I. The rest are all different. Here's the coefficients, and you'll notice by definition, by constraint, as you'll see, there's no sign changes. Positive guys are positive here, negative is negative. Okay? The other thing you notice is that these coefficients are much bigger, the univariate coefficients. I've lost the... either the battery is gone. Oh, that's okay. I can this sort of point. Maybe I'll go over here. So how do we compare these models? Well, first of all, there's a test set here. The predictive accuracy is about the same. So the first thing is I was surprised by this. I do the lasso and I love the lasso, right? I have this model, and now you're telling me there's another model that has very little overlap with the first model, like only 2 markers in common, and it predicts about the same. Well, how can, that's unsettling, right? And you have a different, that'd be useful. Thank you. But that's just a fact of high dimensional problems, right? And correlation. Thank you. And this new color. Okay. So you can have models which are very different. You had a question? Go ahead. Why do I? Oh, up here? Oh, that's a good point. So okay, let me get to that. Okay, so the 2 things you see is that this model is sparser. It's got fewer markers, but I'll answer the question. And you'll see, I haven't even introduced the method yet. You'll see it typically has far fewer than the lasso. Typically, it's maybe a half or 2/3, which is good, I think, okay? But also has this property that you don't get any sign changes, right? And this model tends to be more stable. Now, why is that? So I like to liken this to, I play basketball. Maybe I should use baseball as the analogy, but suppose you're putting a team together of 12 baseball players, right? Let's forget about the signs, but here's team A, here's team B. Team A has got, these guys are all strong, but these 2 players are only really made it in the game because they're correlated with other guys just the right way, right? They're not star players on their own. Whereas these guys are all strong, right? And the method we're seeing, I'll show you, by design, it'll choose things which have higher univariate strength. So there's 2 properties we're seeing, no sign changes, and kind of a Bayesian prior on the coefficients. So the things that are strong on their own, like age, are encouraged would tend to be stronger in the multivariate model. They'll get a boost. Okay? And they're both properties that I think are reasonable and attractive, right? Again, in light of the fact that there's lots of different models that you can pick from. We have to face that reality. So in which case, let's make some assumptions which makes the final model more palatable, more useful, more robust. Now, to answer your question, well, I guess maybe I don't have on the thing. In the lasso, you can, of course, move along the whole path, and you can simplify the model to the point where there's only 8 or 9 predictors like there is in the bottom. It does worse in prediction error, quite a bit worse. So these models are just not differing in sparsity. They're actually in very different parts of feature space, right? We see that because the markers only overlap by 2. So, okay. So that's the intuition. And now, this is a summary of the talk, which I may get to everything. I'll finally tell you what the method is. I'll give you the lambda equals 0 case. This is really interesting. It's competitor to least squares. I'll show you. This is very interesting because we didn't expect this to happen. We thought of it later. Some examples. I may talk about a bit of theory, use of univariate scores, and some other topics. So let me. This work, by the way, is evolving still for other models, and it just got published in the last few days at Harvard Data Science Review with discussion. I'll give you the reference on the last slide. So just to step back, what do we want to achieve? We want to achieve a method that guarantees the signs of the final coefficients agree with the signs of the univariate coefficients, or they're zero. We're not allowing sign changes. I say caution because whenever I talk about this, and in the discussion, Larry Wasserman, who is a good friend and was one of my early students, he's really quite critical of this. Like you can't do that. That's like that breaks the rules of multivariate regression, right? But he's right technically, but I think for high dimensional data we have to think differently. We have to move away from things which we're married to for smaller data sets and relax the assumptions. I'll talk more about that. And the second thing is that what I said, the features with larger coefficients on their own should be given a boost in the final model. So if you're strong on your own, like age, you're more likely to be strong in a multivariate model. Okay. Okay, so let me finally say how we achieve this. It's pretty simple. Here's the idea almost. So it contains most of the ingredients. There's one thing missing. But so we compute the least squares estimates, the univariate least squares estimates. Okay, usual. And then we fit the lasso now with no standardization, non-negativity constraints to the target and the scaled features. So we scale each variable by its univariate coefficient, and we're now going to pick theta with a non-negative constraint, which you can do in GlimNet. So what's going on here? Well, what this does is this essentially changes the units, right? If something like age has got a very big coefficient, and I multiply x by that, that's going to make age very large. That x times beta is very large. And now it's only going to take a very small theta to enter it in the model. So it's like a change of units. It's changing age from days to years, right? And now it only takes a very small multiplier theta to enter in the model. So it gives it an advantage. There's the prior coming in. And the non-negativity constraint is it doesn't allow a sign change, right? If beta's had is positive, multiply it by a non-negative number, I can't get a negative number. So that's it. And then after we select lambda like cross-validation, we compose the model. We just, put the beta and the theta together and we get a predictive model, just like we do with the lasso. This almost works, except that we overfit because the data is being used twice, right? Y is being used, Y and X for this step and this step. So there's information leaks from step 1 to step 2, and this overfits quite badly. So we needed one fix. I guess I say that in the next slide. Yeah, you've already used the data, we get severe overfitting. The fix is to use leave one out coefficients at the first step. So what is this? This is for the jth feature, we leave out point I for every I and j. That's a whole matrix of coefficients, n by p. And they go in here, along with the intercepts. This is what we do. And by using leave one out here, it avoids the leakage of information from step 1 to step 2. So overfitting doesn't happen. This really is important. And you might think, gee, that's a lot of computation. How can we do this? Well, in least squares, there's very nice formulas for this, exact formulas. And for other models, there's nice approximate formulas. So this is all very computable. There's our package called Unilasso, which you can try right now on CRAN. It's all there. And then again, we form the final model. So that's the main idea of the whole talk, this optimization. So I'll pause here for questions and then drill down into more details. So it's the back, yes. With selection of lambda, well, selection of lambda will affect the signs of the final model, but the sign change is more to do with, right, the correlations between variables, right? If things are uncorrelated, there's no sign changes, right? Then the multivariate coefficients are just a univariate coefficients. So it's really correlation. But lambda will tend to change that too, but it's mostly the correlation. Okay. Okay. So that's it. It's basically compute leave one out coefficients, use them as scaling factors in a non-negative lasso. Okay. This I've kind of said. I said this, the fact that the leave one out are really important. There's a relationship to the adaptive lasso and the non-negative garrote. A student asked me earlier what the inspiration was for the lasso, and Leo Bryman's garrote was one of them, non-negative garrote. So this kind of loops back to using a garrote-like non-negative constraint. And we do it for the entire GLMs and survival analysis. It's also kind of a stacked regression, if you know what that is. If you're a machine learning person, we're stacking simple univariate learners together. But those are all connections which you can read about in the paper. So let's just get started here. So what does this look like in practice? Here's an example, we call this the home court, where the method looks quite good. 300 observations, 100 variables, 10% support, that means non-zero, 10% non-zero coefficients, signal to noise ratio about 1, so fairly weak. We see the mean square error is about the same between lasso and unilasso, but the support, the number of non-zero variables, is far less. It's about half. Right? And that's typically what happens. They tend to have about the same mean square error, predictive test set error, but the support is much less. So this non-negative constraint is a very forceful thing that causes a lot of zeros to occur, right? Which is good. You get a sparser model, and you get ones, again, the features, you can all interpret their weights more because they're in the signs you expect. Now, of course, there are severe counterexamples. Like here's an example where I generated two variables which are positively correlated, but their coefficients have different signs. That's exactly the Achilles heel of the method, right? And the error is about twice that of lasso. So it's disaster. But you can tell in a given problem by cross-validation. You just see it. The cross-validated error is also about twice as big, and you say, you shouldn't use this for that data. So you've got a built-in guardrail there. And later, I might get to it, we have a unilasso polish, which basically, if you're in this situation, it can sort of tell you how to correct it. But basically, I think the main point is, no method is a panacea for all problems. Unilasso will often be useful and give you a good prediction and much in sparsity, but sometimes it's going to be really bad. But you can tell that from cross-validation. Okay. Now this is really interesting. I find this was really exciting because it came as a surprise later. You set lambda equals 0 in the lasso, of course you get least squares, right? There's just the L1 penalty is gone, you're just doing least squares. Well, how about unilasso? What happens if lambda equals 0? So there's no L1 regularization. Then we call this unireg. There it is, right? This least squares with these scaling factors with the non-negative constraint, but no further constraint, right? Well, despite the absence of an L1 penalty, you still get sparsity because of this constraint. It's very, very forceful, right? So again, this is a method now where there's no tuning. You give me the data, I give you the answer, just like least squares, right? Well, how does this work? Okay. Well, here's typically what happened, and I'll show you some more, but here's an example, again, n equals 300, p equals 100, 10% sparsity. Here is the lasso path, the number of features as lambda gets smaller and smaller. Lasso, of course, goes up to the least squares estimate, which is saturated at 100 variables. This guy maxes out around 15 or so, right? When the true is 10, or maybe it's around between 10 and 15. So again, it never gets it doesn't overfit. That sparsity, that non-negative constraint really controls it. Well, how does it work? Well, basically, here's a bunch of examples where the story is low, medium, high. Mean square error in all these examples, and these examples are actually smaller, and the support is far less. Look at the support of least squares versus unireg. It's about 10%, a tenth of it. So it gives you a model with 1/10 as many features that predicts quite a bit better. Okay, so I was really excited, and I said, I went to the UC Irvine database, and I grabbed all the regression data sets that were there, and the 23 of them. They're mostly classification data sets, but I do that. And here's a summary of what we found. And there's no tuning here. It's like LS fit or LM in R. It's just a function. You give it the data, out comes the answer. Here's the mean square. Here's the ratio of the mean square errors, least squares over unireg. One being the same. And you see, so least squares wins down here. Unireg wins up here. And you can see it's pretty much of a wash, right? We win in these two cases, but otherwise they're pretty close. The sparsity is it's about, averages 1/3 that of least squares. So on average, on all these data sets, we have about the same mean square error, but with 1/3 the support. And there's no selection going on. It's just like, so I think this is really interesting. It's like a serious competitor to least squares, which, it's been around for 100 years or something. Yeah. So this was a surprise that came out of just starting with a lasso and now moving to the simpler situation with just regression. And as I'll say, maybe at the end of the talk, I think this univariate guidance idea is actually maybe a general paradigm. And I have students that are working on it in other, like for boosting, for interaction models, for neural networks, because in all these problems, you've got a search problem. The search is a challenge to find a good model among many possibilities. So using univariate strength to guide you, I think could be maybe a good general paradigm. We see it working here pretty effectively, right? Among two solutions, pick the one whose univariate coefficients are bigger and whose signs agree with your multivariate signs. That sounds like it's a sensible, I think, approach. It seems to be useful. Again, let me stop for questions because I'm not going to finish all the material anyway, so. Okay, what's next? Oh, car price example. Do I do that? Okay, well, I will say this much. So this is an example. These are car prices, auto prices from UC Irvine. A small data set so we can drill down and look more. 25 features, 205 cars. And here's again the lasso, unilasso. And you can see unilasso is far sparser, and there's all these sign changes in the lasso, right, if you don't like them. But here's another way to look at it. What I did was we took the data and we did many, many half samples. So we took half the observations as a training set, the other half as a test set, and fit on the training set, predicted the test set, did that many times. And here's the results. Test error, I haven't described the polish yet, but it's the blue one. They're around the same. The support of unilasso is far less, right, as we've seen already. The number of violations, how many times does the univariate and multivariate signs differ? We know it's 0 for unilasso, and it's quite common for lasso. The stability is a little bit higher for, what is stability? I looked to see for every pair of fits, how much overlap was there in the variables that are selected. And we see it's a little higher for unilasso. And I've done other experiments where it's quite a bit higher. So I think that's a really important property. If you fit to half the data twice, and you get very different models, it's like, what's going on here, right? So a method that gives you something which is more stable over different half samples it's more trustworthy, right? And that seems to be in other simulations. We see a little bit of it here and more in other simulations. It seems to be really the case because it's leaning on these univariate strengths as a guidepost kind of, right? It's saying, it's not so much just correlation. Now we're going to say, if you're strong univariate, we're going to use that to guide our fit. And that's a more stable kind of thing than just regression correlation. Okay, well, for those of you who know about the lasso, one of the things people look at is the orthogonal design, case where the variables are uncorrelated, in which case there are no sign changes, as I mentioned in response. And all these methods, ridge regression and lasso, have an explicit solution, right? They don't need to do any optimization. The ridge regression is just a proportional shrinkage. So you take the least squares estimates and you shrink them down by a certain factor, depending on the lambda, the ridge parameter. So here's a 45-degree line. Here are the ridge profiles for different lambdas. Lasso is a soft threshold. So it's not a proportional shrink, it's a translation. Every coefficient is translated towards 0 by a certain amount, depending on the lambda. So this is hard threshold. This is ridge. This is soft thresholding. Unilasso is interesting, has this kind of shape. It's kind of it says big coefficients I'm going to leave alone, and smaller coefficients I'm going to make shrink to 0. And it's interesting that other approaches like the MC+, which is popular of Zhang, it explicitly starts with something like this, but it's non-convex. So it makes it really hard to optimize. This just comes out of the algorithm. So it's very convenient. And this is, I think, an appealing shape of thresholding. So it's more evidence that this is maybe sensible. I'm going to compress 30 pages of theory into 3 bullet items, but this is what Shorov did. For those of you who are interested, who know about the lasso, there's a huge body of work on the lasso that says, when does it work mathematically? And the useful condition for support recovery and mean square consistency. So this means, getting choosing the true features that have non-zero coefficients and mean square error consistency is that the non-support features are not too correlated with the support features, right? Which makes perfect sense. You have a model where you've got, in the population, you have non-zero features with non-zero coefficients and the ones with zero coefficients. If they're highly correlated, you're sunk, right? Because if there's correlation 0.99 with the support feature and the non-support feature, the lasso can't tell them apart, right? That's why this condition is needed. That's the irrepresentability condition, mutual incoherence. And of course, there's a very nice theory that makes this official, but this is the basic condition. Unilasso is very different. It's not at all this. He's proven a theorem that says, well, the univariate and multivariate population coefficients have to have the same sign for each feature. Well, that's kind of self-evident because we assume that. But what's really interesting is that the sufficient condition is that for each variable in the true support, if they're positively correlated, the population coefficients have to have the same sign. Otherwise, they have different signs. That's really you have 2 variables which are highly correlated in the population. Their multiple regression coefficients have to have the same sign. So this is, of course, the counterexample I showed you, it violated that. But this is very interesting. This is what really all you need. This is sort of the secret sauce of the method, that if this occurs, positive correlations mean the same sign and negative correlations mean different signs. That is what makes it all work. And the theory it's really impressive that he can be able to prove this. But so for those of you interested in the more mathematical parts, the paper has all the details. Summary over, yeah. I said this already. We get test set accuracy similar to lasso, but with considerably sparser models, with this additional property of no sign changes. Here's another thing we're working on with UK Biobank. But here's a setting. This is, again, I work with people in genetics at Stanford, and they use the UK Biobank, which is a large set of data on SNPs and other things for about 500,000 patients and 1 million SNPs for many different phenotypes, very widely used around the world. And the goal is to build a predictive model for a phenotype like heart disease or cancer, for example. People often apply the lasso, and we have software which allows us to fit the lasso to that big a data set. It takes a few hours, but it's doable. Well, a common situation is that someone, you're studying a disease and you've collected, well, maybe you have the biobank data or you've collected your own SNP data. Someone else publishes a really big study, but with many more patients than yours, but they won't give you the data. This is very common because their data took them years and a lot of money to collect it. What they publish is the univariate scores for each SNP. They won't give you the raw data. Well, what we can do, and we'll show how it works. So we're supposed to have a training set T, that's our data, external data that does not contain the raw data, but only the univariate scores. What can we do with that? What we do with it is that step 1, where we computed the scores internally, we just use external scores in step 1. As a prior kind of, right? We just put the scores from the other guy's model, we put them in at the first stage. So does that work? Well, here's a simulation that suggests it's promising. This is mean square error. This is lasso and unilasso. And this is, this is just on our training data. And here unilasso has a small advantage over lasso. Now, plus 50 means I've taken 50 external scores from the external data. And you can see, in unilasso, the green shows the improvement I get by using the external scores. The red shows if I actually had access to the external data in full, I'd do even better. But this just shows that there's potential in using external scores to improve essentially get more data. And now we've actually done this with real SNP data from Biobank. I don't have it here, but it's showing good results. We have some data on asthma from the Biobank, but we also have a collaborator in Finland who's given us scores from a much larger external data set. And when we put the two together, it does better than the models just on the regular data. So, I mean, it makes sense, right? We're using this as a prior. We're using external scores as essentially as a prior in step one. It was really simple, and it seems to be effective. Time for questions. I'll just say a little bit about, again, I sort of mentioned this, but I think this univariate guidance. So we've completed this paper. We have software, which you're welcome to try, and I'll show you the. Oh, so it's this journal, Harvard Data Science Review. So they don't normally publish methodology papers. Whoops, but Xiao Liming was really happy, was very nice about it, and he liked our paper, so he invited us to. So this is in the latest issue. They asked me for a fancy graphic to show off the lasso, so I was proud of myself. I mean, I just found one on the web. Here it's coming here. Where is it? There it is. Isn't that neat? So, but there's there's the paper, but I was going to just show you the discussants. Do we have them? Where are they? Is it labeled here? Oh yeah, here's a list of the discussants. So there's Lucas Jansen. There they go. Lucas Jansen. You can see the names here. Lots of Larry Wassman I mentioned. Bin Yu and student. Anyway, a great bunch of discussions, which, you know, this guy's a cardiologist I work with at Stanford, and he talks about, he's really excited about it because for his own translational research, he thinks it's a really good paradigm. And Larry gives sort of a counter opinion on this sign constraint, but you can judge. Okay. So with random forest, we do kind of a similar thing. You know, if people know random forest, but part of random forest is you sample some of which features to look at, right? You sample a third of the features, and you sample. Well, now we can put univariate scores for each variable, each feature, and then we use a weighted sampling. So something with high score gets a higher chance of being sampled, and that really helps prediction. Gradient boosting, similar thing. Interaction models. That's a longer story, but we have a way of thinking of interactions, a univariate notion of interactions, which I think is really neat. And so again, it's this idea that univariate guidance can be really helpful in fitting high-dimensional models of lots of different kinds. And these are some of my collaborators who have been using it. Oops, let me just. Oh, so there's the paper, but if you just type in Harvard Data Science Review, you'll see it as you just saw it. Discussions are here. There's the software in R, and it's also in CRAN. And then one of my great students has written a Python version of all of this using that Adderley package as the engine. So if you like Python, that's there too, Unilasso. So that's it. I'm happy to take questions.
Thank you for a great talk. Towards one of your extensions on interaction models, I'm thinking of like generalized linear models or graphical models and kind of how this would extend. Your sufficient condition made sense under a Gaussian model where you're looking at correlations as driving some of these sufficient properties. Kind of in a different generalized context, like generalized linear models, but perhaps different underlying distributions like logistic regression or otherwise, or these interaction models. How would you think the theory? Do you have any insights on like how these conditions or the theory might start to play out? I know it's new, but I was interested.
So practically speaking, we run LimNet with a different family. So that just replaces least squares by whatever, you know, log likelihood you have. The theory, don't know. It's actually, I think one of the discussants talks about extending it to GLMs. So look at it, I think, I don't remember exactly, but I think maybe it's doable, but we haven't done anything.
Yeah, because I mean, the sufficient condition made a lot of sense in a Gaussian framework where the correlations are driving a lot of the model. But I was thinking about how things would change.
In GLMs, they still drive the model, right? It does a weighted least squares. Like the IRLS algorithm, there's a weighted least squares, so they drive it too. But there's other components, but basically it's a nonlinear regression model. So I don't know the details of the conditions, but have a look at the discussion.
Thank you.
There's a question up here.
Thank you, Dr. Tibshirani, for a wonderful talk. And it's more, I really want to ask you for a comment than a question about the, does this uni-lasso type approach is really a step to scale invariance in lasso regression? Because there's always a debate, should you standardize your data before the applying lasso? So does this really kind of solve or partly solve the problem?
Well, it's true that unilasso is scale invariant or equivariant, whatever. Scaling doesn't matter whether you scale. But with the lasso, I think it's it's more of a practical question. Like I think there are times when you should standardize, like when the units are different, you clearly have to standardize. If the units of the features are the same, like they're all genes or SNPs, then you have a decision to make. And usually I wouldn't standardize, but actually I would also use cross-validation to guide as to which one ends up with a better prediction error. So it's true that it is invariant, but I don't think that means for the lasso. I don't know if that's a good thing necessarily. Having the choice can be useful too.
I see.
Yeah.
Thank you.
Well, there's a question here. Yes.
Yeah.
Hi.
Yeah, Dr. Tibshirani, thank you so much for an interesting talk. And I think I speak for many people in the audience that we have been using lasso and enjoying it. And it's great to have you here and listen to you talking about the new developments. And I actually have two questions, if I may. The first is kind of related to Jonathan's question earlier about the interaction. So as you said, the sign change could only happen when there's enough correlation or interaction between the predictors. So that means lasso and unilasso will be different if there's somewhat say graph structure among X. So I'm just curious, do you think it's possible to use the difference between lasso and unilasso to somehow guide us in estimating the graph among X?
Well, the graph, what kind of a graph? We're talking about
So like
Yeah.
if X follows a normal distribution
Yeah.
and we want to estimate the precision matrix.
so we're talking
And-
about, a correlation graph or a precision graph? A graph with
Yes, that's so either like can
Yeah.
we learn something about the correlation structure or the precision among X based on the difference between the two?
well, I think the information's all in the correlation matrix. I don't know how, like, bringing in Y has anything to do with, I don't know how that could help. The information
Mhm.
is in the correlation matrix, and there's no additional information that unilasso and lasso are both using that correlation, but they're not
Mhm.
providing extra information. So I don't see that.
Okay. Okay. Then my second question is about the last comparison you had when you have the external score.
Mhm.
I'm guessing for lasso you only fitted on the training set T, and you
Yes.
and the external set is not used.
Yes?
So I'm curious about whether we can use that because, for example, if say X are standardized mean 0, covariance 1, then the correlation is essentially the covariance between X and Y. And we know in the least squares estimator, we have X transpose X inverse X transpose Y. So can we augment that correlation part from the external data to make lasso better?
So in what you just said, are the X's uncorrelated now?
No. So they are correlated. I'm saying, so you say
I see.
on the external data, you have the correlation, but not X and Y.
Oh, okay, right.
So I'm just saying, can we get that correlation and say, for example, a naive way would be average it with what we get on the training set and use that
Oh,
to
because
improve lasso.
You
as
don't know
well.
the X from the external data.
Yeah.
You're going to assume it's the same as that in the training data? Is that
No. I'm saying we have X transpose Y, which is if everything standard is essentially the correlation between X and Y. So that's the correlation
if
from
it's standardized? It's
the external
it has to
set.
be orthogonal. X transpose X.
X transpose
Well,
Y.
X transpose Y is the correlation between X and Y. Yeah.
Yeah, from the external data, can we
Yes.
use that to augment our estimate on the training set?
But I need to know X
also
transpose X for the lasso, right?
Yeah, we don't know that, but
Yeah. So
yeah,
I don't,
I guess
I don't
yeah.
think that works.
Okay.
I was going to make another comment, which is this.
Mhm.
I think sort of stepping back, I think, we have sort of traditional statistics where P is not very large, right? And the regression's great and all these, we understand confounding correlation. And then we have, these very large data sets like the SNP data set.
Yeah.
And like Larry Wasserman in his comment, if you read it, is basically saying you guys can't establish causality here between features if you make this assumption, which is true.
Mhm.
But I'll say, if you start with a million SNPs and you tell me to build a predictive model, there's no way I'm going to be able to say anything about causality,
Mhm.
like that SNP number 7 is causal, right?
Mhm.
It's more you're trying to explore. You're trying to you're trying to pare down the million SNPs down to maybe a few hundred or something,
Yes.
right? And then the next step would be to do more refined experiments, and I think that's what this is really useful for. It's like the
Mhm.
intermediate thing where I
Mhm.
can't.
Mhm.
I have too much to deal with, right?
Right.
And I can't, I'm nowhere near establishing causality, but I want to pare it down to some good suspects.
Mhm.
And those suspects are things we're saying have the same sign as their marginal correlation, right? And that's,
Mhm.
I think, pretty reasonable. It's
Mhm.
possible that you need other things in there, but
Mhm.
with such a sea of variables, you can't know everything about them. So anyway, so
Thank you so much.
you're welcome.
I take advantage that I'm close to her, so I'm
Okay.
asking the next question, right? So going to car prices, your example.
Yes.
Do you have location as a predictor?
No, I don't think so.
Okay, so-
Geographical location? No, I don't think so.
Yeah, because I think, I was thinking, do you have any model for type of a lasso, unilasso, where the predictor is not necessarily linear, like on the surface of a planet?
You can put in other coordinates. You can put in,
I mean,
uh,
I've seen
Yeah.
some recent papers, but
you
not
could
very
put in
convincing.
two-dimensional coordinates, and you could put a smoothness function. You could do that, yeah. We haven't done that. We didn't have the information there about location.
Because it's
Yeah.
a great difference. Okay, thank you.
There was another.
I hope this works. Can you hear me?
Oh, there.
So I'm just trying to understand this, your formulation. I have it on my phone.
Have it on your phone. Well, I have it on the slide, so here we go.
Right. Just the optimization where you leave one out and write this one.
Yeah.
So just trying to understand this. Let's set lambda equals to 0. That's the easier case.
Okay, here we go.
Right. So the results show that you still get some sparsity.
Yes.
I'm trying to understand the identifiability between thetas and the beta. They are just simply multiplicative, right?
Yeah, but the betas come in from they're already, by the time you get here, they're already defined.
Right. Betas are fixed,
They're
but
fixed, and this optimization is over theta. So,
right. So I'm trying to understand why the theta times beta hat with leave one out doesn't just simply give you the beta you would have gotten if you have used all the data somehow.
remember the beta they're univariate coefficients. So they're not using they're using different data. They're just using feature J. Solve that goes into these guys, right?
They're using different data sets,
Well,
right?
They're only using the jth column. They're univariate. And then here I do a multivariate calculation, right? They're all there, right?
So can I think of the original betas as directions and thetas are simply scaling these directions?
As directions. Well, they're directions. They're numbers, positive or negative,
Okay.
with magnitude. So, I mean, you should think of it. Another way to think of it maybe is in the case of unilasso, that won't help. It's really just a scaling, right? So again, the same thing. If this guy is very large for age, for example, it's gonna make the units beta hat times x, call that z or something. It's going to be very large. And now when you have this penalty, right, it's going to tend to again favor things which have bigger units, right? Because these are non-negative. It's got a it's interesting. It's not really as clear as in the lasso case where you can talk about a budget, but
Yeah, I mean, isn't there an identifiability issue? It's just you're multiplying betas, which are numbers, with thetas, which
Yeah.
are also numbers.
yeah, but the optimization, the betas are fixed at this point. they're known constants. There's nothing, the optimization here is over theta. So they can't be unidentifiability. We've already, you can't change these. These are, think of it this way, to call this Zij.
Right.
It's a new variable, and then there's no beta at all. That's all it's doing. Okay? Right, think
Okay,
about it.
think about it. Yeah.
There's another, yes.
Yeah.
Yes, sir.
Thank you so much for this great presentation. This is probably a very naive question, but I think that in the UniLasso, it is very tempting in the univariate model to change it for something more flexible, for example, for a polynomial or like using some basis functions like splines.
Yeah. True.
Is that
Sure.
possible? Yeah.
Of course, you can use whatever. You can do transformations of the x's first. Yeah. You could do a, we're actually looking at that too, that you can do a version of sort of spline smoothing with univariate, but then again, it's not clear the signs want to be the same. You can do it, but whether it has any meaning is not clear, right? Because what does a sign of a B-spline mean anyway? Like it's sort of elusive, right? But it's possible, yeah. You have a question. You're allowed to have a question? Okay. Okay. Yeah, welcome.
I wonder if you would get accused of being Bayesian in these analyses
Ooh,
and like
around here I might, especially.
what? Yes, we had many meetings with Bayesians
Yeah.
today.
Oh, yeah.
Like I'm trying to figure out what the Bayesian analogy would be of this. You know, it's just inputting prior information.
Yep.
And if we could just formulate that in a prior, then I
Yep.
wouldn't have to go through this leave one out sort of calculation to correct for double use of the data, right?
Oh, it's kind of complicated, right? Like, first of all, the betas are a function of x and y. So the pure Bayesian would not, like, you can have them wrong. The pure Bayesian won't let you compute the prior can't be a function of y, can it? Like, I thought it's something you'd have before you see the data. So-
You're correct there.
So,
Yes,
But
strictly
maybe an
speaking.
empirical Bayesian would get away with it or something, right? And you could use these quantities as prior somehow. So there may be a Bayesian version, but we'll say this is very tractable too. Like that, we can, once you're in the convex world, there's such an advantage over Bayesian. Bayesian methods are great when you can compute them, right? But they're always, I think they're always non-convex. So you have a MC, and it's complicated. This thing is convex, which means we can fit it to like 1 million variables in a reasonable amount of time. So convexity is a huge advantage here. But not to say, it would be interesting to see if there are Bayesian methods which are similar and tractable. Yeah.
And so we didn't get very far with the inference.
Mhm.
And I'm thinking that because you seem to retain the magnitude of the coefficients better with Unilasso, that we might feel like the results are less biased compared to Lasso. Do you think?
Oh, I don't know about that. There's still the shrinkage. I don't know.
Yeah, but maybe not as extreme.
Maybe not.
shrinkage.
Yeah. Yeah, it's true. Well, the models are sparser, so there's probably less overall shrinkage. That's a good point. Yeah. I haven't looked at that. There's another question.
I guess I'll just, though, again, thank you for the talk. It was very interesting. I guess I am more just wanted to get your thought of one thing I could see you wanting to do, right, is if you're doing some feature engineering, you might have a bunch of features that you know are correlated and you want the Unilasso to be applied. Then you might have some that you're agnostic. So you might not want to apply the Unilasso and just have a typical shrinkage possibly, right? You might not want to force it to be the same. That might be a bad example, but I'm just kind of curious, are there cases where you might want to combine this Unilasso prior to some of the coefficients, but not to all of them?
That's interesting. Yeah. So you're kind of, you think you want to be free to have sign changes for some features, but other ones you want to apply this constraint. That's interesting. I mean, I haven't thought of that. You could, of course, just construct this to reflect that, right? So that this is what I do for a feature I want to constrain, and the other ones I just leave them alone. It's interesting. But you want to make sure the scale. Well, that would sort of be giving a coefficient of 1 to there'd be a scaling issue, right? Now it's going to matter really how to scale the data, because
So you have to be
that's interesting
careful.
to see whether that would be doable and useful. Yeah.
Thank you.
A couple questions from the chat, if there are no more questions from you all. All right. So first, should we stop using lasso and switch to unilasso?
Good question. So I would say no. I would do them both. I would use them both, and other things too. Yeah. I mean, again, with cross validation always as your guide, because sometimes, well, I showed you an example where unilasso was disastrous, right? Where was that? Yeah, at the bottom of this thing. I mentioned it was here, right? And this example here, this is disastrous. So you want to have them both in your toolbox. Try them both, and use cross validation to help, and also the interpretation of the model to guide which one you use.
Perfect. Thank you. The next question, given the previous comment about external data for the univariate scores, has there been any work examining unilasso from a Bayesian perspective, priors on theta, etc.?
Priors on theta. Well, maybe did the Zoom people would have heard your question? Or anyway, so yeah, there may be, as we discussed, there may be a Bayesian version of this. I'm not sure and how the prior would be specified. Somehow it has to be a function of the marginal correlations, and it has to be computable. But it'd be interesting. This is doing maybe a poor man's Bayes in a sense, right? It's using scaling factors as priors, but that's very convenient because the computation is still easy. There's no integration over stuff.
Thank you. The next question, instead of univariate models, can we do a one-at-a-time analysis where predictors are one biomarker and covariates? Can we use the beta hats from these one-at-a-time models?
Where you have one biomarker and covariates, and you want to use beta hat from the. Can you say the last part again?
Yes. Can we do a one-at-a-time analysis where predictors are one biomarker and covariates?
Yeah.
Can we use the beta hats from these one-at-a-time models?
I don't know why you want to do that. The purpose of this is to choose among many different biomarkers. If you only have one biomarker and covariates, I think you just want to do least squares. I think can't quite see how that makes sense.
Next question. Would we expect differences in unilasso performance if the intercepts are omitted from step 1 univariate fits? Example, no intercept univariate fits are used in step 1.
You mean in step 2? I think you mean step 2. But I think that, well, I compute them in step 1 and I use them in step 2. I'm not sure what the question was, but I'll answer just in step 2. They're very important. This surprised us that you need to put these here. But the point is, when you leave one out, sort of create a shift in the regression line. So intercepts, for subtle reasons, are really important. It doesn't work as well without them. Yeah.
Any other questions?
You guys have to ask some questions. But I was hoping you might understand something.
All right. Thank you so much.